Well, hello, my friends. Welcome to Module 8, and in this module we will examine linear regression. Lesson 1 is an introduction to linear regression. Simple linear regression is a model used to make a prediction. And simple linear regression is about representing a set of clustered data points with a best fit line. And the line of best fit is a line which represents the data set with the smallest distance between the line and each of the data points. And for linear regression to work, the data set must have two variables that are reasonably correlated. So when we start doing linear regression, one of the first things that we're going to have to establish is that the data points, or the two data sets, are reasonably correlated. They have a correlation which would allow one to be used to predict the other, since they are correlated. A linear relationship can be used to predict a y value for a given x value. I want you to consider this diagram just a moment. This is a coordinate axis, and we have a line in blue, and the line is represented by the equation y equals a times x plus b. We will find out in a minute that a is the slope of the line and b is the place where it crosses the y-axis. But a linear relationship is about being able to plug in an x and then find the y that forms the point where x and y are on the line. For example, we take an x value and use the formula y equals ax plus b. And with that, we predict a y value such that the point x and y is on the line. And that's true for every x value. There is a corresponding y value, and those points map a line under this equation, y equals ax plus b. Now, for the line equation, a and b turn out to be very important. We will come back to those in just a minute. We're going to talk about another issue that we use in linear correlation. But a linear correlational study, or linear regression study, lets us put an x in and we can predict a y value such that the point is on this line. Now, there's a little bit more to it than that, but I want you to look at this. Given the formula y equals ax plus b, if you find the values of a and b, a predictive model is constructed to help you find a y value for a given x value. In other words, you can plug in an x and y, an x into the formula, and it will predict a y. And that's pretty powerful. The y value is the predicted value for a given x value. Now, the value that you plug in for x is called the independent variable. The value that you get for y is called the dependent variable, because the value of y depends on the value of x that you plug into the formula. Now we're going to learn a few more terms about linear regression, and then we're going to bring this all back together again. To find the equation of the best fit line, y equals ax plus b, you must find the equation that best fits the model for using x to predict y. This is called the best fit line and explained in the following slides. The best fit line is found by minimizing the scatter between the linear model and the data points. Now, consider all these data points just a minute. This line represented in blue has scatter from the data points. In other words, scatter is the distance of the data points from the line. See, they're scattered all over the place. And this data set has a lot of scatter. The regression model is considered to be very weak. This data set has very little scatter. And you'll notice that the best fit line goes on the points, and you have very little scatter between the points. And this is said to be a strong regression model. Now, simple linear regression is about representing a set of clustered data points with a best fit line. The line of best fit is a line which represents the data set with the smallest distances between the line and each of the data points. For linear regression to work, the data sets must have two variables that are reasonably correlated. Now, simple linear regression is founded upon the concept of a linear function. A linear function is a line, And it has an equation, y equals ax plus b, such that if you plug x in, you produce a y value. Every x has a y paired to it. In a linear function, an independent variable x is used to produce a dependent variable y under a very specific methodology. Linear regression, accordingly, has only two variables, an independent variable and a dependent variable. Now, I want you to consider the following. Here we have an x-axis and a y-axis again. We draw a line. This line is graphed by an equation, y equals a function of x. And what that means is that you plug an x in under a rule and it produces a y value. Y equals a function of x is the same thing we can say again in this occasion, y equals ax plus some value b. If we plug an x1 into it, it produces a y1 such that the point x1, y1 is on the line. If we want to plug in something else, we can do that, but here we have an x1 plugged in, it produces a y1, x1, y1 is on the line under the equation y equals ax plus b. Now, a is the slope of the line, we'll talk about that in just a minute, but b is where that line crosses the y-axis. So we're in pretty good shape. The slope of the line is the change in y. From this point to this point, y went up that much over the change in x. X changed that much. That's called the slope. So there's the change in y, there's the change in x. From the b-intercept all the way out to this point that we have identified. Now, y equals ax plus b. A is the slope of the line, and b is the y-intercept. Only two things are needed to define a linear function. The two requirements are the slope and a point, and our point in this case will be the y-intercept. When you find the slope, a, the slope, and b, the y-intercept, we can give a prediction formula for it and any point under the formula, y equals ax plus b. Now, the goodness of fit is about choosing the line with the smallest distances between the prediction line and the actual data set. The data set requires a reasonable level of correlation between the independent and dependent variables. In other words, if they're not correlated, a correlation means they have a relationship. If they have no relationship, then the linear function or linear regression is meaningless. Note that the goodness of fit line is only valid between the lower and the upper bounds. One cannot speculate about values outside these boundaries. Now, let's take this picture just a minute. We have these data points represented in some sort of relationship between the x independent variable and the y dependent variable. The lower bounds is the lowest value, and the upper bounds is the largest value, and the only place that the linear regression really has meaning is between the lowest value on up to the largest value. Now, people will try to use linear regression to go beyond the upper bounds and predict the future, but actually that's flawed because linear regression has value only between the lower bounds and the upper bounds. Now, we have a lower bounds and an upper bounds, and we might draw a line. Now, look at this line just a minute. This line is a bad fit line because it has all sorts of scatter. This line is a better fit line because the scatter is not quite as much, and this is the best fit line because the scatter is minimized. The line of best fit is what we're trying to identify. And we want to come up with it under the formula where we know y equals ax plus b. We need to find a, which is the slope of the line, and b, which is where it crosses the y-axis. The goal is to establish the best fit line. This is the line that produces the least amount of scatter between the data points and our model line. Again, this line is a bad fit, this is a better fit, but this is the best fit. This line best let us have the least scattered from the data points. And when we find the formula of the line of best fit, then we can put an x value in, and we can predict its corresponding y value. We can predict the y value using that equation. Once identified under the formula y equals ax plus b, values of x can be predicted between the lower and upper bounds of the data set, but values of y, we put in an x value and it produces a y under the formula ax plus b. Now, we've got this, and we're going to let SPSS do the work for us. But I want you to remember some things. We're looking for the equation of the line of best fit for the data. The line of best fit is the line that minimizes the distance from the model to the actual data points. And when we find that line, we will find its equation and have the formula y equals ax plus b. And then we can plug in an x value and we can predict a y value. So we can use it to predict between the lowest value of x and the highest value of x. Now you've got this. You're rocking. All we have to do is learn how to use SPSS to input our data, how to tell it to do a linear correlation so that we find, first of all, we establish that there is a correlation, and then we establish what the value of A and the value of X, value of A and the value of B actually is. Good luck. You've got this.